So we just learned a bit about Doppler effect by way of watching it and listening to it. So we did a bit of Doppler effect for sound. But in order for us to actually understand some of the cool applications of Doppler effect, you really have to know it a little better than just what it sounds like. So we did Doppler for sound, and actually we saw that with the cars. Now we're going to check out just the Doppler for all things. We did Doppler for sound. Now we're going to do a Doppler, what we call the wave view. And then we're going to look at applications. We'll look at a few examples. So the cars is just a cool thing you notice. You don't really do anything with that. But Doppler wave view. So what does that mean? Well, with the car situation, basically, we can make this, we'll leave that. This can be Mr. Gruber's car that we just watched, and that car was making sounds. So let's see here. And when it makes sounds, the horn on the car is here in the front, and so it essentially blasts the sound this way. But of course, no matter where you are, you hear it, because sound is a wave, and waves spread out, aka diffract. So though the sound is made in one particular direction, it doesn't really matter. It's like throwing a rock at a pond. If you throw a rock, let's say here's a pond of water over here. If you take a rock and you toss it in, it doesn't matter which way the rock came from. The rock hits and makes a splash, and that splash does not just go forward. That splash, actually, you'll see, it makes a circular pattern that spreads out. And so the circles, you end up getting these ripples that look like this, spreading out, to the edges of the pond. Same thing happens with the sound here from the horn. So Mr. Gruber's horn, though he projected it one way, the sound actually traveled in all ways. And so it spreads out, it diffracts as it goes. So this is now, a second later, you have this pattern, a second later, you have this pattern, a second later, you have this pattern. And so these just keep spreading. And so no matter where you're standing, like Mr. B is over here on the side of the road. Let's say the road was this way. Mr. B was standing over here with the camera listening. Well, those sound waves would come and right along this line, hit him in the camera. Okay, so this view here, this wave view, we often call this the aerial view of waves. That's going to be helpful to us. So let's check out what's really going on with this wave view with the Doppler effect. So here we go. We have basically three situations. We have situation number one, which is the simple situation, and that's basically everybody's sitting still. So at the beginning, we had Mr. Gruber's car blasting the horn. We had Mr. B standing over here with the camera. Here's his little phone camera. And the horn, as the waves spread out, we had wave, and then it would spread out, wave, 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 and so on. And so every time one of these wave fronts bumps into the camera, and then another one bumps, and another one bumps, this all happens very quickly. The frequency of the horn is probably somewhere around, let's say 400 hertz. What that means is a new compression of air hits the phone 400 times per second. And that also means from your own ears that the little eardrum is also shaking back and forth 400 times per second. So anyway, this is when the car is sitting still. And so the car is playing, let's say, 400 hertz, and the phone and the person are hearing 400 hertz. It's all good. So that's situation one. Now, situation 2 is when the car is actually driving toward. And when the car is driving toward Mr. B, something interesting happens. You see, here's Mr. B over here. He's got his little phone. Listen to this, Joe. All right, so the car, let's see if we can draw this nicely. The car makes the first little sound, there it is. Now, if it were sitting still, it would make the next one and the next one, and you see the spacing here. This spacing would come out the same. These should be evenly spaced. But in this case, something different happens. The car drives a little bit forward. So instead of sitting here, this wave now would expand out to the next wave. This one would, with time, it actually spreads out just like it did up top. And it would be, here's where it spreads out to, and now it makes a new one. But here's the cool thing. The car actually drives a little forward, which means the next wave it makes is actually going to be here. Whoa, the picture looks a little different now. And if we wait again, what happens is this wave will spread out. So both of these are going to spread out. So let's try to color code this just right. This little one is going to spread out to here. 1 will spread to 2. And 2 is going to spread out to 3. Except the thing that's happening all the while is as they're spreading out, so this one has spread, this one, the car continues driving forward, which means this next new one that gets made, it's a little hard to draw on here, chalkboard would be much nicer, is actually going to be over here. And so what ends up happening is all the waves on the front side of the car, you see this whole area over here, all the waves in this region get squished together. And what that means is they're squished together, and as they approach Mr. B squished together, you're actually going to have a pattern more like this. You know, it's going to curve all the way around too. But check it out. Before, Mr. B was only getting 400 bumps per second. Now he's getting more. Now the frequency that he hears, and his eardrum will actually shake at something bigger, like maybe 500 hertz, 500 shakes per second. The car horn is still making 400, but they're getting to you quicker because the horn is running at you. This is actually situation 3 at the same time, because if Mr. B were back here instead, let's say the car has already driven past him, if he's back here listening, in this case, the waves are actually running away from him. Look at this big spacing. They're running away from him, which means he's getting less than 500, less than 400. Maybe he's only getting 300 hertz, 300 bumps per second, 300 shakes of that eardrum per second. And so the crazy thing here is that even though the car makes the same exact 400 hertz, the person that it's driving towards will actually hear a higher note. And that's what you saw in that video. And the person it's driving away from will actually hear a lower note. And you saw that in the video too. When the car approached you, and then when it went past you, that's the Doppler effect. So the car itself has not changed. It's still playing the same 400 hertz. But if it drives towards someone, they will hear a higher note. You actually hear a higher note. And when it drives away from someone, you actually hear a lower note. That's really the essence of what's going on. So why do we care about this? Because we got a couple of quick applications of the Doppler effect. All right. we have, let's see, there's one application of sound, and then we're going to have two applications of light. So really, I guess you can say two applications of sound. One from sound is just kind of like fun to hear. And the second application of sound is actually called a sonic boom. And I'll show you some videos of a sonic boom. We're not going to get too crazy into it, but a sonic boom is basically this. If Mr. Gruber's car were able to drive, let's see, we'll draw it a few ways. If Mr. Gruber's car drives slowly, and here's Mr. B over here listening, you don't need the camera this time, you can just listen with your ear. And we're going to see if we can duplicate this thing. Maybe not. Okay, if he's driving slowly toward Mr. B, what you'll actually notice is the waves will be a little more crunched on the front side than they are on the back side. See if I can move Mr. B closer. There we go. So he's going to hear a higher note. However, if Mr. Gruber were to drive really fast toward Mr. B, here's a second situation. So instead of driving slow, now he's driving fast toward Mr. B. Here he is. Still listening. The waves will be more crunched. So it'll be something like this. And I should run out of little room for drawing here. But basically, the waves will be more crunched together. So in this case, you had a high note. In this case, you had a higher note. And then there's an extreme scenario. The extreme scenario is, what if Mr. Gruber's car were able to drive at the speed of sound? What if his car could drive so fast? It can't, but there are cars that can do them. Well, I'll show you a video of like a car, and it doesn't really look like a car. What if it could drive so fast that it kept up with the sound waves themselves? That sounds kind of crazy, but that's basically you need a car that can go 750 miles per hour. So, if Mr. Burbett's over here listening, if you have a car that could go that fast, you actually get all these little wave fronts here, all these little lines stack on top of each other. You actually get something that looks like this. And this forms a sonic cone over here. And when they actually come up and hit the person in the ear, you actually hear a sonic boom. It's really loud. So this is an application you can use to figure out how fast things are going, and it's also something that planes have to be mindful of because it's really loud. And so you don't want them doing this over where people live. Watch a couple videos of that. Application of Doppler effect with light. There are two cool applications I'll tell you real quick. One is police. Police radar gun or speed gun, however you want to call it. Basically, here's how it works. Policeman sitting over here, and you are over here driving. Let's say you're driving toward the policeman. This is pretty cool, actually. Check this out. So I'm not going to draw the full circles. I'm going to keep it a little simpler. Policeman actually points a radar gun at you. We'll put his radar gun right here. Points a radar gun at you. Aims it at you. Shoots it at you. And it's shooting microwaves generally. Instead of drawing the full circles all the way around, I'm just going to draw little pieces of it. So here it comes toward you. And it does diffract, so it spreads out a bit. It's heading in this direction. It actually hits your car. Now, let me line it up so it looks a little nicer. they actually aim for your car. In fact, a lot of them have sights. They can sit and aim. And the part they like to aim at the most is your license plate. Why? Well, because look at what they want to happen. They want this thing to come, hit your car in the license plate, and then what? Well, it doesn't get a reading from that. They want it to, let's switch up the color. They want it to hit your license plate, and they want it to reflect back. Oh, why is a license plate shiny? They're always shiny. So it reflects light. Now, what kind of light does it reflect? Visible, yes, so you can see it. But it also reflects microwaves. And that's what the police take advantage of. And here's the cool thing about it. When it hits your car, if the car is moving toward the policeman, it actually intercepts these wave fronts. It intercepts these. So here's 1, 2, 3, 4. Sooner than it would have if it were sitting still. And it sends them back. It reflects them back. Now, why is the license plate flat? So it's like a mirror. You want a flat and shiny object as the license plate so that it actually just sends the light back. And it sends them back. I'll draw them this way now. This, except because it's hitting them quicker, it's going to send them back quicker. So like 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And what happens is the radar gun, once these get back and they hit the radar gun, boom, the radar gun says, wait a minute. The radar gun actually has a little computer in it. I sent 4 in a second. It's not really 4. And I got back 7 in a second. And it does a little math. And it says, boom, there's an equation for this. If you want it, you can look it up. I could tell it to you, but it doesn't really matter here. It does a little math with these two things. And it says, boom, that car is moving toward me at 60 miles per hour. And it shows up on the little screen up here, 60. And if the speed limit is 45, the policeman's coming for you. You're getting a ticket. That's it. So the Doppler effect for light is how police actually issue tickets. Pretty cool, huh? All right. So if the car is moving away, you get the same sort of thing instead of toward, except it would get back fewer. Maybe it would get back only 2. Sent 4, got back 2, and it could figure out it's going 50 miles per hour away instead of 60 toward. By the way, this is the same exact thing with baseball. So if you have a pitcher and they throw the ball, and here's the catcher, the radar gun always has to be either back here, aimed at the ball coming toward it, or behind the pitcher, aimed at the ball going away from it. The radar gun can never be over here on the side, pointing at the ball. No, that wouldn't work, because in that case, the ball is not going toward or away from the radar gun. It's just going past it. So the speed will reveal 0. Okay, the last application of the Doppler effect is also a light application. It is, what do we call it, 2, 3, I don't know. Astronomy. A cool thing you should know about is you learn this in earth science, but people say that, oh, the universe is universe is expanding. Well, how do they make that claim? How do they claim this? Well, basically, here's Earth, and here are some other galaxies somewhat far away, not too far. These are, you ever go take an astronomy class, they'll have you draw galaxies like this. These are spiral galaxies. Not all galaxies are spiral galaxies, but all right. So if you have a bunch of galaxies, and you look at them. These galaxies give off light, and the light comes to Earth. The light goes in every direction, of course, but some of it comes to Earth. And so what do? We're like, all right, man, pop that telescope. Put a telescope over here and over here and over here. You got to aim at all the different devices. There are a lot of telescopes on Earth, and all those telescopes get the light. And it's a little fancier than what I'm going to show you here right now, but basically when you look at that light, what you notice is that for many galaxies, the light appears redder, more red than expected. And what redder really means, it's a little fancier than we need to worry about right now, but what redder really means is lower frequency. And if you remember from lower frequency with the cars, that means moving away. So really the prime piece of evidence people use to claim the universe is expanding is known as, and they taught you this in earth science, they call it the Doppler Red Shift. And what that means is when we put our telescopes on a lot of the galaxies that we can see, not all, but a lot, we notice that the light appears lower frequency than we expect. And because we understand the Doppler effect, lower frequency means they are moving away from us. So if all the stuff is moving away from us, well, that means things are expanding. And if things are expanding, that means once upon a time they were closer. And if once upon a time they were closer, well, what is that? We have a name for all that right there. In science, this brings us back to what we call the Big Bang. One of the origin explanations. How did the universe start? There's a lot of complication with this, but the Doppler effect is something discovered by Hubble, 1929, I believe, in America. So this has allowed people to say, oh, wait a minute, because we understand it, because of the lower frequency, because that means things must be moving away, they must have been closer, they must have been condensed, there's some sort of Big Bang that led to the universe spreading apart. Pretty cool, huh? And a continuation of the astronomy part, and I mention these not because you have to worry about any heavy testing, I promised I'd be lighter on the questions on these, I will, is continuation of the astronomy, is this is actually part of how people have figured out some of the planets around other stars. So just to give you a little reference, here's the sun, here's the Earth, and then maybe somewhere far away, we could even change the color a little, far, far away, this drawing is lousy, here's some other star, and there's some other planet going around that star. So we'll call that planet P. And so if this planet is going around the star, an interesting thing happens with the star. The interesting thing is these two pull on each other by gravity. So the planet pulls the star and the star pulls the planet. Now the planet, it's obvious to see the effect of the pull. It follows this path. But the star actually moves a little too. So if the planet is over here, the star gets tugged a little this way toward it, just a little. And if the planet is instead over here, the star gets tugged a little bit this way. And this repeats. So it gets tugged this way, then this way, then this way, then this way. Now from Earth, you could put up a big old telescope as big as you want to try to see. Say, what's going on over here? I want to see the light of this star, and here comes the light of this star. It really is those wave fronts we were talking about. Here comes the light of this star. Will we see the star wobbling back and forth? No. We can't see the wobble. It's too far away and the movement is too small. But we can see something, and this is pretty cool. When the planet is lined up here, the star gets tugged a little bit, switch up the color, this way toward Earth. And when the planet's in the back, the star gets tugged a little bit away from Earth. Oh, so when the star is tugged toward Earth, guess what? You get Doppler effect. This is crazy. Yes, actually, the waves appear a little bit more squished together than they normally would. And we actually call that a blue shift, opposite of a red shift. When the star is tugged away from Earth, you get the Doppler effect too. Actually, you get like we talked about before, the red shift. And so if your fancy telescope, it has to be attached to a computer, your eyeballs cannot see this. If your fancy telescope is attached to a computer, looking at a star, and it sees this pattern, in the light that's switching. Let's say here's what you expect the normal color to be, right here. But you actually see a little bit of a wobble in the color. You actually see it going like this. Whereas anytime it's up here, it's looking a little more red. And anytime it's down here, looking a little more blue. Then you're like, well, why is there that pattern? Why are we seeing it a little redder, a little bluer, a little redder, a little bluer? Oh, we can't see. And guess what else you can't see? You can't see the planet either. But you can see the effect. You can't see the planet, but what you can see is this pattern. Red, blue, red, blue. And red shift, blue shift, red shift, blue shift. And if you see that, what would cause a star to do that? Stars don't just do that. Oh, has to be a planet around it. Though we can't see the planet itself, like a footprint from a bear in the woods. We know there's a bear there. You can't see the bear, but you can see the evidence that it was there. And in fact, by judging the size of the print and the depth of the print and all the moisture of the soil, you could figure out the mass of that bear. You could figure out information about it. Here, judging by the size of the star and amount of wobble, amount of red and blue shift, and how long it takes, you can figure out information about that planet. And so when scientists tell you they discovered planets around other stars, other places, other solar systems, it's not as crazy as it sounds, but you should understand where they're coming from. Doppler effect is one of the key pieces of evidence.